Good morning, everybody. Thank you for being here at this side event to the 56th session of the United Nations Statistical Commission, in which the joint testing UNCPD, UNCAG, joint testing on Earth observations for agricultural statistics will share with you the main activities that we have working in the last year. Because we have short time for all the items to see in this meeting, we will begin with the first item. In the first item, we have the opening remarks by the chair of the UNCPD, Mr. Ashwell Jenneker. Ashwell, thank you for being here with us. Welcome, and the floor is yours.
Thank you very much, Eduardo. I'm Ashwell Jenneker. I'm from Statistics South Africa, and Statistics South Africa is the chair of the UN Committee of Experts on Big Data and Data Science for Official Statistics. So I'm speaking to you from Pretoria. It's 32 degrees Celsius now in Pretoria. We've just had a thunderstorm start, so it's cooling down a little bit. I was in Kazan last year in Russia, and I see it's 0 degrees in Kazan. In Paris, it's 1, and in New York, it's 0 degrees. And so these are the challenges we've got around the globe when it comes to the issue of food, because climate is integrally linked to food security. And we as statisticians, we've got a responsibility to provide the best up-to-date statistics to those in the agricultural industry. And this is why we're here today, to talk about how do we do this. So let's talk about the Committee of Experts. The Committee of Experts was established in 2014 by the UN Statistical Commission. And the responsibility of the committee was to look at big data and data science for official statistics, and to see how could we use big data and data science to advance our official statistics. Now, the Committee on Earth Observation was also started in 2014, and they were very active right from the start. In fact, their first report that they produced was in 2017, and they focused on Earth observation and how can you use satellite imagery. For example, when we do the census, we look at how things have changed on the ground, and we also use satellite imagery to demarcate the country before one will do such a thing as a census. Now, gradually, the Committee on Earth Observation moved more towards the use of agricultural statistics. And therefore, they joined with the UN Committee of Experts on Food Security, Agriculture, and Rural Statistics, called the UNCEAG. Now, that was in 2020. These two committees combined forces. Now, in 2022, this joint task team produced the second report, and they looked at Earth observation and how it can be applied in agricultural statistics. And this was delivered at the UN Statistical Commission at the time. Their third report is now ready in 2025. And the committee is looking, in the third report, they're looking at the applications of agriculture statistics, and they're also looking at use cases. So I would recommend that you read this report, very detailed report, 81 pages of it, and they look at use cases in Austria, Brazil, Finland, Indonesia, Mexico, and Poland. And they're also looking at capacity building activities on this topic within Senegal and Zimbabwe. Now, these practical applications show how far this field has come in applying AI and machine learning on satellite data. And this helps us on various issues like crop yield forecasting and early crop season estimates. Now, these are the types of things that gives us current data, relevant data to work with. I would especially like to thank Eduardo and Lorenzo for their leadership in these committees. I want to remind you that this is not Eduardo and Lorenzo's work. This is not their primary job. So they mostly, like all the 100 other experts that work in the committee, is volunteers that volunteer to help and to look at AI and look at machine learning and see how we can apply this. Now, your efforts, Lorenzo and Eduardo, is really appreciated. And this definitely takes us forward in this interesting endeavors. With this, I wish everyone a very interesting, fruitful, and enjoyable webinar. Thank you very much.
Thank you as well for your kind words about the joint task team. And to leverage the time, we will move to the next item. The next item is the presentation from Lorenzo about the introduction of the joint task team program work. Lorenzo, the floor is yours. Thank you for being here.
Thank you very much, Eduardo. Good morning and good afternoon, everyone. I will briefly provide a short introduction of the task team, highlight some key advancements and trends in Earth observation data and how the team is embracing those, talk about the expanded thematic areas of the work of the task team and some highlights of the report. So as we know, the history of the task team is based on the fact that UN Statistical Commission recognized Earth observation data as a cost-effective granular alternative to traditional surveys and censuses, especially for monitoring agriculture and SDG. The origins are really in the big data transformation sparked in 2014 by the Statistics Commission, which led to the establishment of the UNSC56, so the Committee of Experts on Big Data and Data Science for Statistics, to explore big data applications and address quality and confidentiality. The initial focus of the task team, it started as a task team on satellite imagery under the Global Working Group on Big Data. And then it was targeting crop yield prediction through representative training data. Then there was an expanded scope. And so the task team was renamed Task Team on Earth Observation Data for Agricultural Statistics to encompass a broader range of Earth observation applications. Some milestones. So in 2017, there was the foundational guidance on Earth observation data use, satellite imagery and geospatial data task team report. In 2020, the restructuring led to a joint task team under the UNSC56, but also under the UNSC, which is the Committee of Experts on rural statistics and food security, aligning Earth observation application with a broader food security and agricultural statistics priorities. The latest contributions were in 2022, the release of lessons learned and recommendation from selected Earth observation applications on agriculture. And in 2023, we launched also an Earth observation methodology knowledge assessment app to support capacity building. The ongoing focus areas, of course, enhancing crop classification, integration of big data, addressing governance, and exploring new Earth observation applications for emerging challenges. A small ID of the task team. So there is there are two co-chairs, Eduardo Vasquez, myself, and then we have a secretariat from Valerie and Ronald. We have the participation of 13 active member countries, and we have 3 new members who are formalizing at this stage their participation to the task team. And we also have 2 additional contributors for the ongoing, for the latest report. Of course, there is a strong support from international organizations. So we have the FAO, the UN Statistics Division, the World Meteorological Organizations, the World Bank, USDA, the Asian Development Bank, the Digital Earth Africa. Evolving trends. So what has been observed in the last years and how this is reflected by the work of the team. So first of all, the first trend is clearly the fusion of multiple Earth observation sensors, especially mixing optical and radar data. Trend number two, more advanced machine learning and AI. Number three, the introduction of Earth observation data cubes, and trend number four, the uptake of more crop yield forecasting models. Some details on the trend number one, essentially the fusion of the radar data with optical data. It's because radar data can operate also during the night and then during the day. It can see through clouds. It has higher sensitivity to changes in physical characteristics, shape, height. So for example, it can inform on the height of the crops to differentiate small crops from high crops, for example. And fusing this data with optical data increases the density of our time series so we can better describe phenology and hence discriminate. But beyond the optical data, there has been actually an increase in the use also of other sensors, for instance, Sentinel-3, MODIS, and very high resolution data like Planet Labs. And we can see here, for example, Austria is using both Sentinel-2, Sentinel-1, Brazil is using Sentinel-2, Sentinel-1, and Planet Labs. Finland is using the Sentinel-2, Indonesia is using Sentinel-2, 1, and MODIS, actually, and also, Planet Labs. Mexico is using Sentinel-2, Sentinel-1. Poland is the only country who's using for the first time the three constellations, so Sentinel-1, 2, and Sentinel-3. Senegal has been using both Sentinel-2, Sentinel-1, and Zimbabwe Sentinel-2. Of course, it depends on the conditions. It doesn't always add value to have more data, but we can see that compared to the last report, 2-3 years ago, we have much more data richness, let's say. Trend number two, the increase in use of machine learning and artificial intelligence is because we tend to find ways to extract temporal features in a better way so that then we can enhance the accuracy because we can discriminate better. We can have more robust tools to noise and variability, computational efficiency, and to learning capabilities, improve generalization of methods, of models, and more versatile applications. In this chart, we look at a small meta-analysis of the methods used in Earth observations in the last 15 years. And we can see, of course, random forest is the most used one, but we see also support vector machine is also used more than 20% of the times, and down to convolutional neural networks and temporal convolutional neural networks. Those methods use more temporal information. And of course, they have stronger, let's say, prediction power. And then we also have long short-term memory, gradient boosting machines, multi-layer perceptrons, and unsupervised learning, which is usually used as a first exploration of in-crop type mapping. And in the report, you will see reflected the work of Austria using temporal convolutional neural networks. And they're also using causal networks, which means that they're able to predict data just based on past and current information. So it's not dependent from the future data. This is a very strong aspects. Mexico, Senegal, and Zimbabwe use cases are using random forest. Indonesia and Poland are both using gradient boost machines for mapping rice phenology, but also for predicting yield in the case of Poland. Mexico has been using also multi-layer perceptrons. And Indonesia is using the self-organizing maps and k-means in order to stratify their approach, but also to increase the quality of in situ data. The trend in data cubes is essentially because Earth observation data is a sparse and irregular acquisition of images. So we need to regularize this into structured data cubes. And a data cube is defined essentially as a dense raster data cube with a 4-dimensional array. And essentially all the data is structured and regularized across time and space. So this offers the possibility to run time series analysis in an efficient way. As of crop yield modeling, we have 3 main approaches that are emerging. And of course, we have in our report, we have a very good case of a machine learning approach for crop yield model carried out by Poland Statistics. The task team has expanded its scope, as I anticipated. We have introduced disaster risk reduction because of drought and flood impacts on the yield and hence on the statistics. And we know that Earth observation data can support that. We also have added biodiversity because of the impact of agriculture on biodiversity, and vice versa, the role of biodiversity for a productive agriculture. Third, we have the data governance, because more and more in countries, the importance of maintaining Earth observation data cubes, the data confidentiality, and integrating these with field operation is calling for a better governance, which of course has to take also into account the confidentiality of field observation data. And finally, we have increased our collaboration with the regional and global big data hubs. So there are very important initiatives ongoing, among which the organization of regional workshops, webinars, but also actively collaborating into projects in countries. Key takeaways from the work of the task team is that we have an increased sophistication. So we have more advanced Earth observation data being used, like use of radar, for instance, and optical data. We have a broader scope of applications, having more environmental and disaster-related issues being addressed. Enhanced scalability, so the use of data cubes and cloud computing has made these methods more scalable, of course, and efficient. And finally, we have also stronger focus on developing countries, so building capacity in both use of Earth observation data, but also in situ data collection. Some highlights of the report, so just some appetizers. So we have Austria, who's going to present their work on crop type classification using a temporal convolutional neural networks and complementing the land parcel identification system. Brazil is going to present on parcel segmentation for agricultural census planning, and it's going to use artificial intelligence to detect the boundaries of the parcels. Finland will present an early season crop yield estimation for major and minor crops using neural networks. In Indonesia will present on rapid rice phenology prediction using Sentinel-1 imagery and area sampling frame surveys. Mexico will present an open source crop classification method leveraging Sentinel-1 and Sentinel-2 using machine learning. And Poland is going to present the development of a crop monitoring system and yield forecasting model using Sentinel-3 data, MODIS, vegetation indexes, and ERA5 agrometeorological indicators. And finally, we have two presentations on capacity building. So we're going to have a presentation from Zimbabwe Statistics, so leveraging an FAO and African Development Bank support to improve agricultural statistics using Earth observation. And Senegal, I will deliver a small presentation on how to use alternative classification methods, which are more data frugal, to produce crop type maps, essentially when we have scarcity of field data. Thank you very much.
Thank you, Lorenzo, for this very wide scope of the activities in the UN and the joint task team. Okay, let's move to our next item, that are the use cases. And we begin with Abel Coronado from INEGI, Mexico. Abel, thank you for being here. The floor is yours. You have, I remember to all the presenters that you will have only 4 minutes to present your project, and I will let you know when you are in the last minute. Abel, go ahead.
Thank you very much. Good morning. I'm Abel Coronado from INEGI, Mexico. It's an honor to speak at this side event. Today, I will share a research project which addresses the global need for the operational use of Earth observation data in agricultural statistics. Our project aims to improve the accuracy of agricultural data by using open satellite data from Sentinel-1 and Sentinel-2, combined with AI-driven crop classification techniques. This effort is a collaborative innovation between INEGI's Data Science Laboratory, or regional field teams, and Economic Statistics Directorate. By working together, we have developed a robust technology stack that supports both cloud and on-premise processing. This dual approach allows us to handle large amounts of data with great scalability and security. We see this project as a first step in training our team in Python and data science. Our goal is to share our experience and methods so that our team and others can speak the language of the modern data analysis. By doing this, we not only improve our operational practices, but also contribute to better, more accurate agricultural statistics in the country. I also want to emphasize that we have created a comprehensive open source tutorial available on GitHub. This tutorial includes all the code and detailing instructions needed to reproduce our work. It is clear sign of our commitment to transparency and capacity building in the field of agricultural statistics. Our project aims to refine crop classification to improve the agricultural statistics. In the first phase, we convert raw satellite imagery into actionable information by applying Schaeffer segmentation. These techniques divide images into distinct crop parcels, allowing us to extract key features such as NDVI, EBI, and radar backscatter, which serve as reliable variables of the field conditions. By integrating data from multiple satellites, Sentinel-2 for optical imagery, Sentinel-1 for radar, we have built a robust data set that provides a richer perspective on the agricultural landscape. Our preliminary results are encouraging. We have implemented an assembled model that combines a multi-layer perceptron with extra trees stacking, achieving approximately 77 overall accuracy. This model consistently distinguishes cultivated from not cultivated areas, although challenges remain with underrepresented crops due to data imbalance. These insights are essential as they shape our plans to further refine our model and improve overall classification performance. The core objective of this work is capacity building. We have carefully documented our methodology in a Jupyter notebook and developed a comprehensive English tutorial available on GitHub. This open source resource is designated to train our team. Thank you. Our team in Python and data science, laying a strong foundation for future operational statistic data. Our next steps are clear. We plan to extend our core methodology across different regions and crop systems in the country. This will allow us to improve the use of air observation data in official agricultural statistics. In the coming phase, we will integrate additional data resources such as time series data and digital elevation models, and adopt advanced machine learning approaches to further refine our results. In conclusion, our project not only advances the science of crop classification, but also builds capacity within our team and a broader community. We are excited about the potential of this innovation to transform agricultural statistics and support sustainable decision-making. Thank you for your attention.
Thank you, Abel. Thank you for your presentation. And I remember all the presenters, all the audience. If you have questions, you can use the chat to write your question, and please put your name and the name of the presenter to whom the question is addressed. Let's continue with our next presenter. Is the time for Maria Ili-Heikkilä from Finland. I'm sorry if I am pronouncing bad your last name. Please, Maria, the floor is yours.
Thank you.
You have 4 minutes.
Yes. So, thank you. My name is Maria Ili-Heikkilä. I'm a research scientist at the Natural Resources Institute, Finland. And our topic was early season crop yield forecasting with Sentinel-2. So our objective was a high granularity, high accuracy forecast with minimal operational workload. And guided with these objectives, in 2018, we started and we chose to have only Sentinel-2 imagery. And then because our reference data was on farm level, we chose the object-based approach. And then we were predicting yields on field parcel level. And then our method was temporal neural network because it was suitable for time series prediction. And then finally last year we came out with our results and we made our first release of in-season crop yield forecasts, and we called it experimental statistics, and it was well received in media. For example, it was said that the new era of crop forecasts has begun. Then about the applicability of our method. First of all, the method is based on the fact that we know the field delineations and the crop type grown. But it could work in monocultures where only one main crop is grown and the cropland mask exists. Or in other case, it could be used so that the field delineation and crop type classification is run, and then after that we would use the crop yield forecasting. The method is built so that it's scalable. In the future, we will probably have finally hyperspectral data, for example. So this method can be scaled to new data sets as well. And then finally to highlight that the reference data is still golden if we are going to have in the future those large pre-trained deep learning models called foundation models. We will still need local data for validation at least.
Maria.
And preferably also to adjust the model, then we would need also some data for training. That's it. Thank you.
Thank you, Maria. Thank you for your interesting presentation. And let's move now to the next presenter, Ian Nunes from Brazil. Ian, you have 4 minutes. Go ahead. The floor is yours.
Hi, good morning all. My name is Ian Nunes, and I'm the head of Agriculture, Data Intelligence and Innovation at IBG. First, I'd like to thank you for inviting me to present our work at this event. We hope to contribute to the discussion of using Earth observation data for agricultural statistics. Today, I'll briefly talk about the project of parceling the Brazilian territory using deep learning. Before I dive into the project, it's important to understand the broader context it's part of. Our research spans multiple fronts and covers various areas like data science, machine learning, databases, computational optimization, and decision support systems. The Territory Parceling Project is an initiative that leverages remote sensing technology, marking the beginning of a long-term effort to enhance the production of official agricultural statistics in Brazil. In future stages, this project aims to help identify crops and better understand their productivity and production levels. We tested different neural network architectures like UNet, BizNet, SwinUNet, HRNet, and YOLO, among others. We are using all bands from Sentinel-2 and Planet Labs as input for our models. And since we are using a supervised training strategy, we started with several well-known public data sets for training this task. However, after many transfer learning tests with those data sets, we realized that we need to produce labor data in Brazil due to the unique characteristics of the climate, territory, and production. And to build our data set, we relied on IBG's specialists to select the target municipalities, and we also put together a multidisciplinary team to label, monitor, and improve the work. By June of this year, we are aiming to have over 1 million plots and more than 50 cities fully manually mapped. This is a huge milestone for the project and will greatly enhance the automatic mapping process. Given the size of Brazil and the complexity of the task, we plan to continue with manual labeling even after this stage is complete. Today, we already have a complete pipeline for the automatic production of plots of field delineation, which evolves methodologically with each interaction and as more data becomes available. The table shows some preliminary results with the background image displaying plots produced by one of the models. It also highlights the main metrics used, especially the last three ones, which represent error measures. These plots will be used as inputs for the next agricultural census and in the production of agricultural statistics. Thank you.
Thank you, Jan, for your presentation. By the way, we couldn't see any slide if you were presenting. Anyway, all the presentation will be posted in our website.
Oh, okay. You didn't see my slides. Oh, sorry. I shared the screen. Okay.
Okay. Thank you. We will move now to our next presentation. Our next presenter is Ahmad Fauzi from Indonesia. Please, Ahmad, the floor is yours. You have 4 minutes for your presentation.
Okay, greeting everyone. My name is Ahmad Fauzi from Indonesia, and I would like to share you about observation data for paddy crop phenology identification in Indonesia. Okay, first of all, Indonesia paddy productivity of the paddy rely on two surveys, which are area sampling survey for monitoring the phenology and calculating the harvest area, and the crop cutting survey for estimating productivity. However, traditional methods face challenges such as high cost and difficulty in data collection. Therefore, we propose a new modern approach called mixed method, which integrates ASF with the observation data as well as machine learning, helping for optimizing cost-effective data collection, addressing non-response issue, and reducing the surveyor burden. Moving on, understanding the paddy crop stages is crucial for accurate modeling. There are paddy phenology class collected in ISF data, and by doing some adjustment, we're developing several new classes like Berlin for the consecutive harvest. And by using the satellite imagery, which are Sentinel-1, we analyze spectral values corresponding to a phenologic stage, and we can know the unique pattern from that. Okay, moving on again to the methodological part. The first section is the imagery acquisition. We start by intersecting the 10 selected province with a military grid reference system or MGRS, downloading the Sentinel-1 radar data, and then do some processing using Snap, and we produce a result as follow, which is Sentinel-1 with a VH band on 12-day intervals from January 2021 until December 2023 with 20 meters spatial resolution. And before going to the modeling, we believe that due to a large area of Indonesia, specific models based on agricultural characteristics are prominent. Hence, we do clustering on regions area based on several characteristics using scattered clustering. And moving on to the data preprocessing, we do several preprocessing workflow. For instance, is the point cloning, and then do some imputation using with checkered areas, and then do some of variance filtering for homogeneity. And the last one is the self-organizing maps for representativeness. And then after doing some preprocessing, we use XGBoost modeling for get the model of the paddy crop. And lastly, we're estimating the phenological area based on the dot sampling procedure using a survey frame. And the next one is the results and findings. Here it is. As you can see here, it is the accuracy map based on the S cluster. We spot that there are areas that have good results denoted by the green color and the light green, and also there are poor results denoted by the red color. Based on investigation, we found that they perform well overall in general, but struggles in one, a mountainous area with terrace fields, small and scattered rice fields, swampy lowland and dryland rice areas, region with irregular planting patterns. Second, we also compared the harvest area from our prediction with the SF data, as you can see from the graph plot. At the glance, for all cluster method shows similar pattern figures. However, for the area with a lower accuracy, the predicted area tends to be overestimated compared to the ISF results or our traditional results. And we also do some growth truth for checking the true value in the field and our models. We know that there are some room for improvement since our estimates are more fun like in growth truth. And we also know that there are some is unmatched and there's one is unmatched. I think that's all from Indonesia. Thank you for.
Eduardo, we cannot hear you.
Sorry. Thank you, Ahmad, for your interesting presentation. Let's move now to our next presenter from Poland, Artur Laczynski. Artur, go ahead. The floor is yours. You have 4 minutes for your presentation.
Okay. Good afternoon. I would like to present our project. In fact, our system that is working in statistics Poland. I'm coming from development, and I work together with my colleague Przemysław Ślesiński from the regional office in Olsztyn. That we just operating the system that allows us to produce
Artur, I don't know if I am or everybody is having problem to hearing you.
I confirm we cannot hear you. We cannot hear Artur.
Okay, Artur, it seems that there is a problem with your audio. Well, it seems that Artur leaves the room or is still. We have problems to hear you, Artur. Maybe we can move to other presentation. Meanwhile, you
administrative
can...
data of self-collected data. The also in situ self-collected for the crop classification. And what is an outcome? It's a cure.
Yeah, Artur, your audio is
for different crops that we can recognize machine learning. Sorry?
Your audio is cutting.
Okay, so we have a validation procedure as well, and then segmentation. Then we have also the monitoring using NDVI, also the shifting vegetation using a degree, days, and yield forecasts for different crops. We have 36 crops and 11 crops for yield estimates using different parameters of growing estimation. So our conclusion, thank you for your attention.
Thank you, Artur. We couldn't see you. We couldn't see your slides.
I cannot switch on camera, in fact.
Okay, and we heard your audio.
Okay.
Got it, but always your presentation will be uploaded in the website,
Okay.
to be available. Thank you for your presentation, and let's move to our next presenter. From Statistik Austria, Nils von Norsinski. Please, Nils, the floor is yours, and you have 4 minutes for your presentation.
Can you see my PowerPoint?
Yes, we can see you.
Okay. Okay, hello, my name is Nils von Norsinski. I will do a quick presentation about crop type classifications of Austria. So we started with it after visiting Poland last or 2 years ago. And yeah, as remote sensing data, Sentinel-1 and 2 was used, the resolution is 10 meters. And for Sentinel-2, we used data from the vegetation period, March to October, and did a bi-weekly aggregation. So data from 2 weeks are aggregated into one image. And for Sentinel-1, we used the monthly mean of gamma naught corrected data also from the vegetation period. And here, so we have a problem here. The time series have different length. And for the neural network, you need to bring them on the same length. So I did just a simple thing and replaced all missing data and empty images with minus 9,999 to bring it on the same length. And of course, did also normalization. So as the reference data, we use the land parcel identification system data. So these cover not all areas, but many areas, and we distribute 4,000 points per class. And this whole data has 200 classes, and we relabel them to the classes we need. So on the good
Niels, it seems that we have also problems with your audio.
Oh, I was set on mute for some reasons. It's now better?
Yeah, go ahead.
Okay, as you can see, on the right-hand side on the confusion matrix, we have a good classification accuracy for most classes, with the exception of grassland and others, which is under 0.8. And as the neural network, we used also a temporal convolutional network like Maria. And on the left-hand side, you can see the classification accuracy when you shorten the time series. For example, if you use data from March to April, you have an classification accuracy of 0.6. And when you use it from March to May, you have 0.7. So you can see the classification accuracy when you do a classification within the vegetation period, when you have not the complete year. And as a result, we masked out the non-agricultural areas with land cover map we have also done, or you could also use a digital cataster. And a bit problematic are small parcels with an extent of less than 20 meters, because then the pixels are bordering. And to a further step to improve the model would be to generalize it and train over data for more years. And that was my presentation. Thank you.
Thank you, Niels, for your presentation, for an interesting presentation. And with this presentation, we finalized the item from use of cases of studies. And let's move to our next topic, highlighting capacity building activities and applications. We have 2 presentations in this item. The first presentation, our first presenter is Nelson Mupugami from Zimbabwe. Nelson, go ahead. You have 4 minutes for your presentation.
Thank you, Chair. Good afternoon, everyone. My name is Nelson from the Zimbabwe National Statistics Agency. So I'm going to give a presentation on our experience with the agriculture statistics product on how best we can leverage on the 8 of data So basically, I'm going to look at the traditional methods which are being used by NSOs in collecting the agriculture statistics. So the main area of focus will be the sampling frames and the sampling methodology, also as well as the area under crop. So these are areas which we see can be leveraged on the Earth observations methodology. So basically, traditionally, the methods for collecting agriculture statistics, when we're using our sampling frames, they are based mainly on the list sampling frames, which are mostly derived from the population and housing census. And also there's a use of registers from various sources with the registers of farmers as well as plot holders. And in some cases, this kind of frames might have some insufficient information, which is required for sampling. So in terms of estimating area under crops, so the traditional methods which are mainly used by the NSO will be mostly on the farmer expert estimate, where they are giving their estimates based on their experience, and also in some cases the use of GPS coordinates, whereby they are measuring area under crop. And historically they will be using this kind of pacing method. So these are traditional methodologies for estimating area under crop as well as on sampling. So with this on background, we now need to see how we can leverage on Earth observation based on the challenges which we have in these traditional methods for improving the agriculture statistics. So as Zimbabwe, we are one of the beneficiaries for the capacity building on the EOSAT, that is the use of Earth observation data in improving the availability of agriculture statistics. So we had a project on crop typing using the EOStat. So this was mainly to measure the spatial distribution and acreage of crops across the summer and winter crops in Zimbabwe. So for this, the survey design, we resorted to the area frame where the canvas into grid or cells blocks, each measuring 2 kilometer by 2 kilometer. I'm just going to give a highlight of some of the notes coming from the survey which we did. So on this one, the first map was produced using the wall-to-wall on winter wheat, and also a small field survey was implemented to collect samples in sampled districts, and there was a very high accuracy which was scored around 0.95. Then also on summer crops, a map was generated using the Sentinel 2, and this map showing the spread of various crops. Unfortunately, you may not pick it well, but from the map it can be seen that the area was dominated by maize, which is the most common crop in the country. And also zooming on those, we can see that the plots are well demarcated. So let me move on opportunities for leveraging this Earth observation data. So based on the presentation of the sampling methodology, I think there are quite various opportunities for us to leverage on Earth observation data, ranging from the cost effectiveness, the quality, the timeliness, as well as the disaggregation. The Earth observations data will need to improve on the quality of our agriculture statistics. Yeah, thank you, Chair. This marks the end of the presentation.
Thank you, Nelson, for your interesting presentation. Now we will move to our last presenter, Lorenzo De Simone, our colleague and co-chair of the Joint Task Team, will present other high capacity building activities. Lorenzo, the floor is yours. You have 4 minutes for your presentation.
Oh, thank you, Eduardo. So very briefly, this is an activity, a capacity building activity that was started in 2019 between FAO and Senegal. In particular, our counterparts was the Direction d'Analyse et de la Prévision des Statistiques Agricoles, DAPSA, within the Ministry of Agriculture, et l'Agence nationale de la statistique et de la démographie, ANSD, and the Centres de suivi écologique. So we have 3 partners in the country. We've in time achieved different important milestones, like the first national crop type map in 2019. In 2021, we have experimented together an adjusted field protocol to improve the quality of the annual agricultural survey data. And then this was endorsed after the testing in Neoro and has been used in 2024 in 6 districts, and we've developed a series of capacity building hands-on activities. The new, let's say, the new activity that we're going to present today is really that of a research-like activity, which is the experimentation of frugal algorithms that we can use when we still suffer from data scarcity, training data scarcity, or data that has not enough geopositional accuracy. And in this context, we talk about the dynamic time warping. So in principle, we classify crops based on time series data extracted from the satellite images. And so what the time warping does, it really looks for subsequences in a time series by pattern matching. And the advantage of this is that patterns are idealized and data instead is noisy. So we've built an application using Google Earth Engine. So it's available, it's shareable, both the application and the codes, where the end user can upload few training data or can generate these artificially. There are some quality control inside there. Then it can pre-process satellite data. It can create those time series of time series from the satellite data that has been pre-processed, and therefore it can extract spectral signatures which are used as a reference for specific finds the pair of time series that best match, and therefore it's able to identify the type of crop. When tested in comparison with random forest for classification accuracy, we can see that when we're using a very limited number of training data, so 5 training data, 10 training data, 20, and so on until 50, we can see that dynamic time warping performs higher accuracy than random forest, and we need essentially 5-6 times more training data for the random forest to outperform the dynamic time warping. So we consider this as a option B, I would say, as a strategy B for those situations where for any reasons we cannot collect data because of financial constraints, because of pandemics, or because of conflicts. So this has been, let's say, the latest activity in Senegal. Thank you. Thank you.
Thank you, Lorenzo, for your interesting presentation. Thank you all the presenters for your presentations. As you could see, we have seen very different applications of observations. And also, as Lorenzo mentioned before, different use of algorithms and different finality or objectives of this project. So we can move now to the session of question and answers. Please, if any of you have questions, you can raise your hand and to see and to direct your questions. Any hand raised? I couldn't see.
Maybe I can ask a question resonating the ones that have been shared in the chat. So we have a colleague from FAO in particular who's interested in reusing scripts and data and methods. And the question is, are those accessible? So I might take this question and to say that we've tried to switch to a more transparent way to share experiences, in the sense that beside the description of the methods and the result, we also provide a link to the repositories, to either GitHub or to either Google Earth Engine scripts. So by reading the report, there is already links to that. But of course, also inside the presentation, this is possible to find. And another approach is just to send an email to the authors of the presentations. Thanks.
Yeah, thank you, Lorenzo. Yeah, I also remember that in the chat we posted the link to reach the full document, the full report, and also the place where you can find the presentations. Can you see any hand raised? Because I don't see hands raised. Well, I don't see hands. I don't see questions also in the chat.
I think Gordon raised his hand.
Okay. Gordon, go ahead.
There, I had to unmute myself. Sorry. Lorenzo, you're talking about the dynamic time warp and the random forest. The results were better for the dynamic time warp. And if I understood you correctly, it was with fewer data points. Would you elaborate on that? I find it very interesting because it has an enormous implication for this type of work.
Okay. Thank you, Gordon. So let me reshare the slides, the one in particular from the study. Share screen. Okay. So the point here is that, as you know, random forest is a very robust decision tree system. It allows to manage very well collinearity, outliers. The problem is that it's very data hungry. And it's not really a time series based approach, because even if you provide features which are gathered in time, if you switch the sequence of the numbers, it doesn't matter. So the sequence, the order is not important. Instead, the dynamic time warping, of course, looks at the sequence. So it looks at the shape of the time series. And based on that, it does a matching using a non-Euclidean distance. Now, what we showed here is that if we train the random forest and the dynamic time warping with the same data, of course, and we only use 5 to 10 data points per crop, then when we produce the map and we run the confusion matrix using the rest of the data for validation, all of the available validation data or just 30 samples for validation, then we see that the dynamic time warping performs better, which means in the chart on the left, when we only use 5 data points, random forest is around 84, dynamic time warping is around 86. And then when we use 10 data points, random forest is around 84.5, overall accuracy, of course, and dynamic time warping is still around the 86. But then when you look at 30, 40, and 50, essentially, data points, so we keep increasing the number of data, and we train the random forest to see when it surpasses the dynamic time warping. And we see that this is basically happening when we use 30 to 40 data points, which is just like saying we're using 6 times or 8 times more data. Okay, then dynamic time, then the data set used for the dynamic time warping. Now, would I advise to use the dynamic warping over the random forest if we had still the same amount of data? That we should test, that we don't know. But for sure, if we really have just few data points, like 5 to 10, then I would go and look into a time series approach, let's say, instead of a decision tree, because the decision tree, I think, could be more let's say less robust.
Thank you, Lorenzo. Thank you, Gordon, for your question. Anyone else can ask something to our presenters? I don't see more hands raised. So as I mentioned before, you can read the full report where you can find detailed information about every project presented today. And also, as Lorenzo mentioned, you can reach our presenters by email if you have some specific or more detailed question. So we can consider that the meeting is we are close to the end of the time. So Valerie and Ronald, can you add something for our audience?
No, thank you, Eduardo. Of course, like Sophie mentioned in the chat, we will put the recording as well as the presentation of each of the presenters. So I invite the presenter who hasn't sent us the presentation to do it so that we can upload them in the website as soon as possible. But the background report is already published. I put the link also in the chat, and I encourage you, as Eduardo mentioned, to read it and reach out if you have any question. And maybe last thing, if you would be interested to join the task team, you can also contact me directly. I'll put my email in the chat. So that you're welcome if you're interested. We meet once a month with different topic. Of course, we look for active participation to contribute to the various work stream that Lorenzo presented today. Thank you. Back to you, Eduardo.
Thank you, Valerie. Ronald, do you like to say something to our audience? I don't know if Ronald is still here.
No, I think he had to drop it, unfortunately.
Okay. Well, Lorenzo, would you like to add something else?
I'm very grateful for the continued support from the countries, and also today's participation is very rich. We reached almost 80 participants at the beginning. Now we are still 64. So I think it's a reflection of the fact that Earth observation data are becoming more and more used, and there is more interest in the operational use, and NSOs are starting to appreciate the various advantages or use cases for Earth observation data, which can be different. So it's not just about creating maps. It's about disaggregation. It can be about having early estimates that then can be confirmed by the traditional survey-based methods. It can be also to increase the accuracy, to reduce the variance around the area estimation. We had a slide in the presentation from Zimbabwe, but the time did not allow to go more in depth. But essentially, we can think of Earth observation data as a way, as a free open source that can be injected back with the survey data to increase the accuracy without having to intensify the sampling. So there are many, let's say, aspects that are becoming clearer on how to use Earth observation data. So I think it's a very good moment, and especially because now the data is available, there is more wealth of free and open Earth observation data. So I think let's say the broader scope of the team, as documented in the report, is also reflecting this, that the direction, let's say, is about progress, overall progress. So I'm just very pleased with the work of the NSOs and very much impressed. Thanks.
Thank you, Lorenzo. Thank you for your kind words. Well, I just want to say thank you all of you for being here, for hear our presenters. Thank you as well for your opening remarks. thank you all the presenters for your very interesting presentations. And I think that it's all. We can finalize the session. And as well, do you want to add something to finalize? We can hear you.
No, thank you. And best of all, and thanks to all the presenters.
Thank you as well. Well, have a good day, and thank you all of you for being here in this side event. I hope that it will be very helpful for you, and thank you for your presence.
Thank you, Eduardo.
Thank you,
everyone. Bye.